This is a square to round. It looks difficult to make, and all these are made from the same method. It used to be the benchmark for apprentice skill, and it used to be the go-to ask if you mentioned you're a sheet metal worker. It's called triangulation. It sounds really technical, but essentially I boiled it down to one particular simple rule. Let us not waste any more time, let us delve straight into it. As we can see, I've drawn up a representation of this model. That is a plan view. Looking on top, this is the side end elevation. Once I've got my circle, the diameter is irrelevant, and so is the square size. It's whatever you deem it to be, or it needs to be, the parameters. Once I've got my circle, I've divided it up into equal spacings. I've chosen 24, but you can equally choose 12. You can choose. The more you choose, the better it is. The more bends we've got, the tighter and nicer the round will be at the top. I've marked on each corner A, B, C, D, just for reference, so we know where we are when we start plotting the development. On the end elevation, I've marked off there, projected off, vertical height. This is always constant, so this height is always going to be the vertical height. There's plan length for his table of true lengths as we start going through into it. So plan length, why is it different? Why do we need to mark it out? Well, as we see from the model, we could take a dimension off there in 2D on the drawing, but it tows away from us. It dips away from us, it slopes away, and we can't get a true length of what we need. So a true length is anything which is the same in the plan view, dimension-wise, as in the end elevation. So for example, this line is exactly the same line as that, size as that, so that is our true length. So this is where I'm going to start from, this point here. I will measure this line and plot it onto our development sheet. I've just marked the baseline on ready, A to B, ready to transfer our starting points. I'm going to start with this true length here, A to 6, and 6 to B is exactly the same size, true length also. So we take a measurement from here, put a point on A, measure across to 6. I can double check if I wish. B to 6, perfect. So they are both the same size. I'll mark that dimensions as plan length line now. This is essentially X, Y axis. So plan length done, A to 0. We then take a dimension from A0 to his vertical height, which I said before is always as constant. Now armed with his true length, I'll mark it onto A. I like to mark it across the centre line, try and keep everything nice and square. And as it's the same size, we know, mark it on B. And there we have our point. That is the starting point. That is now all. So here we can see we've marked it out. That's his baseline. That is exactly what we're looking at now. That is our baseline, A to B. And these are true lengths, the exact true length of that, even though it's moving away from us. We're just plotting a point from a 2D drawing into a 3D point of space. Which sounds really spacey and that, but it's not. Now, it's just repetition. It's as easy as that. So the next one I'm going to choose is A to 5. Now, as we can see, A to 5 is the same size on both sides. As before, we mark A to 5 on his plan length line. And as before, quite simply, point and a 0.5 up to his vertical height, like I say, is constant. And that again is our true length. As before, we'll mark from both corners because they're both the same. Like an arc. Like an arc. We've got the true length arced in now. That gives us this true length size there, but we need to tie these in. Obviously, it's called triangulation, so it needs to be in a triangle. We've only got one size. We've got that size. We need to get this size, and we get that from our diameter. I take a size of one of these marks. They are all the same, so it doesn't matter which one I take. And with that, I then mark it on. And that gives us a spacing across, and where it intersects that arc and intersects that arc is our next point. This is 0.5, 0.5, A, B, 6, 5 and 5, all marked on, and this is starting to curve around, which will give us a shape. And with this formula, it's a simple case of repeating now for all the points all the way around. So I'll start filling some of these points in. So, cracked on, marked all these points out, and that just gives us this side length and the development around to this point here. The next side is quite easy to form. We've got this true length, which we know is a true length, which is A0, which is the same as this, which is the same as that. So we know it's going to be the same as this side here. Our swing and arc. And then we need the length of this, which we know is a true length. If I swing that arc across there, that is the point of our next side. Next A to D, that's his next size on his base, and that is also the same triangle as it's in there. And this side will be the same as the opposite side, so I'll repeat the process on this side. The development's starting now. We've got 3 sides. We just need to repeat this process around here now to get the curve around the other side. That's all marked out. This is the full length of the circle. These are the 3 sides. We've just got to do the last bit of the last sides. See the plan length, this is where I've put the joint. So what we need to do now to finish it all off, because we've got all the way around to here, is get this true length of the joint. This is a true length because it can measure both in the elevation and in the plan, and it's the same size. Just need to mark these points together to create the last bit on our development. And as a checkpoint, these 2 points, when we come together on here, they should be 90 degrees square. Nicely 90 degrees, so we know it's right. Here we have now the full development all complete. All sides are in, joint line, all these are going to be fold lines. Let's plot this out onto his cardboard, fold it up and see how it looks. Push through onto the card with each point. As we can see, all marked up, cut it out and fold it. There's a round, there's a square, exactly the same, apart from I've filled it in. And that's how we make a 3D model from a 2D drawing. Like I always say, every shape starts flat. Every fabricated piece starts really with understanding space. And once you start understanding space and distance, the shape reveals itself.